So now that you've read the notes, you've seen the basic idea of Romberg integration. Use the trapezoid rule with 2 to the n subdivisions as the initial estimator, taking advantage of the fact that the error term has even powers of h as far as we want. Then apply Richardson extrapolation to combine these estimators and get the best possible numerical answer. So there are other ways to code this. For instance, the book chapter posted below has a more traditional Fortran type way to code it. But I think in Mathematica, when you face something that's defined recursively, you should just program it recursively. So this is the way to do it that looks most like the math. So the 0, 0 estimator is the trapezoid rule with 2 to the 0, that's one subdivision, which is b minus a over 2 times f of a plus f of b, period. Now the n0 estimator, that is the trapezoid rule with 2 to the n subdivisions, is just b minus a over 2 to the n plus 1, that's h over 2, times the sum of terms spaced out by b minus a over 2 to the n. But we remember that for terms with an even index, we already computed those function values as part of the previous Romberg estimator, the trapezoid rule with half as many intervals. So in fact, we can save ourselves a little bit of work by remembering the value of the previous estimator and only adding in the calculations at odd steps that we need to get the next version. Okay, once you've defined all of the n0 estimators that you need, to get the nm estimator, you just use the Richardson extrapolation recursion. So Rnm is some term times Rnm minus 1 minus some other term times Rn minus 1m minus 1. And finally, the kth order Romberg estimator is the one k minus 1, and that will have step size 2 to the k. It will have 2 to the k subdivisions in the final k0 estimator that we use to compute k minus 1. So I'll just define that. And then we're going to talk about this kind of interesting coding construction here. Why does it say Romberg n0 equals Romberg n0 equals? Okay, so here's the idea. If I call a function that looks like f of pattern delayed equals f of value immediate equals something else, if f of that value is not already defined, it evaluates this whole statement. That produces the result, and as a side effect, it also permanently defines f of the input value. That means that another call to f with the same input will immediately replace f of x with whatever you computed without rerunning the code. So for example, here's a function that has no inherent meaning. I just defined it because summing a million things takes about 1.3 seconds on my laptop. So I'll notice that if I run it again, it has to recompute everything, even though I gave it the same input. And it again takes about 1.3 seconds. On the other hand, if I define it with this caching construction, this is the same function, then the first call takes about 1.3 seconds. But if I call it again with the same input, it's almost instant. Now, of course, if I call it with a different input, it takes 1.3 seconds again because it had to compute g of 4.0. But if I evaluate it again at 4.0, it's instant, and it hasn't forgotten the value at 3.0. Recovering that is also instant. Okay, so now we're just going to recover the previous trapezoid rule, and I'll define the trapezoid rule of order k to be the trapezoid rule with 2 to the k subdivisions. So again, this thing is h over 2, and I'm summing up f of a plus everything else with a 2 plus f of b. Okay, and now we're going to compare the performance of the trapezoid rule with 2 to the k subdivisions with the Romberg rule, which depends on the 2 to the k subdivision trapezoid data. So here is our h, b minus a over 2 to the k for the trapezoid rule. I'm just going to compute it in crazy precision. Here's the Romberg error. I'm going to call Romberg integration of order k. Again, the h here is b minus a over 2k. And we'll try the integral from 0 to pi of sine of x. So we're going to do it from order 2 to order 7, which is to say from 4 intervals to 2 to the 7th. That's 128 intervals. Okay, here we go. All right, I got trapezoid error, I got Romberg error. Notice they take essentially the same amount of time. Now the trapezoid rule is supposed to be O of h squared. And indeed, if I linear fit log h to log error, I get something with slope 2. However, the Romberg error has no fixed power, right? The power of h goes up with the order k. And in fact, we'll see that it fits really quite well to this quadratic. So if we look at them together, we see that, and I guess I'll make this a little bigger and get rid of the palette so we can see the labels. We can see the trapezoid rule error with a certain number of subdivisions going down, at least in the log-log plot linearly. This has slope 2. Again, the axes are very differently scaled. But the Romberg integration error is going down quadratically as a power of log h in terms of log h. And you can see that by 2 to the 7th intervals, only 100 intervals or something, we've already got 20 correct digits. This is despite the fact that we are in no way in one of the special cases where the trapezoid rule does particularly well. There are no matching derivatives, it's not a periodic function, and yet Romberg integration dramatically outperforms the straight trapezoid rule. Now, it's reasonable to worry that Richardson extrapolation can only be carried so far. And that's fair. For instance, if you look at this subtraction, you could have nearby values here that are being subtracted from one another, and this part of the computation could become numerically unstable. So let's see if that actually happens here. So now we're going to go ahead and do the calculation, but I will carefully do it in machine arithmetic by multiplying everything by 1.0s and eliminating the extra precision. So here's the machine arithmetic trapezoid error and the machine arithmetic Romberg error. And I'm going to go from 2 to the 2nd, 4 intervals. Here I'll go all the way to 2 to the 8th, 256 intervals. I get data. There's no real theory for this because round-off error will play a part. And you'll notice here that uh, Romberg integration still does very well, even in machine arithmetic. Now, we'll never get better than about 10 to the minus 16 in double precision arithmetic. But you can see that the machine computation of the Romberg integration really round-off error plays very little role. The total error is very close to the approximation error. As we get very close to 16 correct digits. Of course, the trapezoid error, both approximation and total, are essentially the same in this region, and you can't see any difference whatsoever. Okay, so you should wonder about computation speed. So if I look at the timing for the order 7 trapezoid rule and the order 7 Romberg integration, you can see that Romberg integration appears to take about twice as long. Now, this is to some extent an artifact of Mathematica coding. I could do this with power 9, and I could do this with power 9. And you can see that the additional layers of recursion do cost us slightly. However, for most cases of numerical integration, it's not doing the recursion and storing the results that takes time. It's actually evaluating the function. So how can we count function evaluations inside the trap and Romberg integration code? Well, okay. The first thing we could do is look at the code and prove a theorem about it, which is completely fair. Another thing you could do is rewrite the trap function and the Romberg integration function to increment a counter whenever you evaluate the function. Or maybe you could redefine the function to increment some global variable, calls or something, every time it gets evaluated. So this is not, neither of these are terrific plans. So in the first place, we might not have access to the trap or Romberg integration functions. For instance, if we were using nintegrate, we really couldn't go inside nintegrate and cause it to increment a counter everywhere the function was evaluated. Either the coders of Mathematica built that feature in or they didn't. Similarly, if we use a global, well, globals are trouble. You have to remember to reset it to 0 every time you call the function, every time you call Romberg integration or trap. You have to avoid having the same name as another global, or you have to explicitly limit the scope by writing everything inside block or module. So Mathematica provides a nice way to do this for sort of communication from deep inside other functions with functions called so and reap. Okay, so if you think about this code evaluates the sine function 10 times. Now, if we replace sine with this function, so a 1, and then evaluate sine, it still evaluates sine 10 times, and it still gives you the same result. So it appears that the so did nothing. However, if you enclose this whole call in a reap, what happens is you get a list. The first entry in the list is the output of whatever's inside the reap. And the second entry in the list contains everything that was sowed inside the calls to the function. And note that you don't always have to sow a 1. Like, you could sow the number, in which case you'd get back the arguments that were passed to sine. Now, I'm just going to sow 1s for an example. It means to me that the function was called once. So here, if we want to know how many times the function was called, we have to take the length of the list in the second argument uh, of in the second position of the thing returned by reap. So length of reap21. And you can see that when we do that, we count 10 evaluations when we run it from 1 to 10, and 15 evaluations when we run it from 1 to 15. We didn't have to reset any globals. We didn't have to go inside the code here. The things we sewed are all cleaned out when we reap them. Okay, so we're going to use the same construction for trap at order 7 and Romberg integration at order 7, just to count function evaluations. So trap at order 7 has 128 intervals, so it evaluates the function 129 times. Romberg also evaluates the function 129 times. Now, one of the things this tells you is that we wrote Romberg carefully. We evaluate exactly as many times as we need to, and we never evaluate the function twice at any one point. But this also tells you that Romberg integration should be just as fast as the trapezoid rule, at least when the time spent evaluating the integrand is the dominant time it takes. Okay.